Hello, I am Subroto Camillo, working as a teacher in physics in Women's Polytechnic, Kolkata, and I am going to discuss the relevant topics of the Unit 2 of the syllabus, that is force and motion. Well, as you see, the syllabus is listed at the top and the learning outcomes at the below. You can see it later. Now, let us start with Newton's laws of motion. Here are the three laws: first law, second law, and third law. Have a revision on these. Now, though Newton's laws nicely explain motion of objects, as we observe in our everyday life, they have certain limitations also. These are something like this. Number one is they are valid in inertial reference frame only, but not in non-inertial or accelerated reference frame. However, second law can be applied to an object in non-inertial frame by considering a pseudo force. And number two is they are not applicable to relativistic observer or an object, that is observer or object moving with speed comparable to the speed of light. And the third one is they do not give accurate answers of problems related to subatomic particles. Now here is a table of four fundamental forces, namely the gravitational force, electromagnetic forces, strong forces, and weak forces, with their relative strength as shown in the table. Well, next comes, let us have a look of the first law, which gives us two important concepts. Number one, the inertia of matter, and number two, the qualitative definition of force. Go and have a revision on inertia of rest, inertia of motion, and examples, and qualitative definition of force. Now, two important points regarding first law is that the term external force in the first law means the net external force, that is the vector sum of all the forces acting on the body. The second point is that the state of rest represents zero acceleration. Likewise, uniform motion in a straight line also implies zero acceleration. That means if the net external force on a body is zero, its acceleration is zero. So, from the point of view of the cause of motion, we can say that both the state of rest and the state of uniform motion in a straight line are equivalent. Well, next comes a very important term, what I call momentum, which represents the quantity of motion of an object. Let us take an example. From our common perception, we can say that in order to bring a heavy vehicle at rest at a particular stopping distance, the opposing force required to be applied not only depends upon the velocity but also on the mass of the vehicle. This observation led Newton to introduce a quantity defined as called linear momentum, which is defined as P is equal to mv, product of mass and velocity, which is obviously a vector quantity. As you see, the units and dimensions are given over here. Well, next, second law. Let us have a discussion on second law. This gives the quantitative measure of the force. Let us see how. Well, the impressed force F is directly proportional to rate of change of momentum. P is the momentum at the instant t, so the proportionality constant K is there. Then finally F comes out to be K time derivative of product of mass and velocity. Now, look at this equation. This is the very important equation, which is the most general mathematical form of Newton's second law. Forget about the constant K, because this can be made to be equal to 1 to define unit of force. Now, take a special case for a system of constant mass. In that case, m can be taken out of the derivative and f reduces to a form something like kma. So, this form is a special form of Newton's second law. Now, for a system of variable mass, that is example, say rocket propulsion, f will contain two terms, km dv dt plus kv dm dt. Now, this dm dt stands for the rate of change of mass with time. It is the second term of the above equation which actually provides the required thrust to the rocket for forward motion. Now, here is the definition of the unit of force from that given equation, that F is equal to Kma. If we choose K, F1, M1 and A1, then K becomes 1. And then this is the definition of the unit of force. And this unit is called the Epsilon unit. Finally, we arrive at a very famous equation in the history of science, that is F is equal to ma. Now, here we should have a very critical look on the definition of unit of force. Now, you see, the force is defined in terms of the equation F is equal to kma, second, which is the form of second law in special case. The question is, shouldn't we define unit of force in terms of most general form of second law, which is this one, F is equal to k dp dt, because this is the most general case of the second law. Well, I am leaving this topic upon you to think. Well, next comes the salient points of the second law. As usual, the term force in the second law means the net external force, and the second point is something like this: the equation force is equal to ma. This is applicable to a particle, that is for a point mass. Now, for a body, say a rigid body, or for a system of particles, F stands for the total external force on the system, and A represents the acceleration of the center of mass of the body of the system. Well, now it is the third law. We like to have a discussion. Let us consider a system comprising of two bodies A and B. Then the force exerted on A by B is equal but opposite to the force exerted on B by A. This is shown by this equation. Obviously, we can conclude that, number one, whenever a force acts on a body, there always exists another body on which an equal and opposite force is exerted. That is, in nature, forces always occur in pairs. Any one of the pair of forces can be called action and the other one as reaction. The second one is that action and reaction act at the same instant, and hence action cannot be treated as cause and the reaction as the effect. There is no cause and effect relationship implied in the third law. And the third one is action and reaction always act on two different bodies and hence can never produce equilibrium in a body. However, if we consider the two bodies as a system, then these two forces are interpreted as the internal forces of the system, and then we could write FAB plus AB is equal to 0. That is, you can say internal forces in a body or a system of particles cancel away in pairs. Now, here comes another important term, what we call impulse of a force, which is defined as the product of force and time of action of the force. And obviously, it's a vector quantity. Now, let us see what it comes out to be finally. As we see over here, that the impulse of a force is product of force and time. And if you break up force into acceleration and then in terms of velocity, it finally comes out to be mv minus mu, which is equal to the change in momentum. Similarly, we can show that even if for a variable force, I comes out to impulse comes out to be equal to change in momentum. That is, we can say whether the force is constant or variable, that is immaterial. Impulse of the force is always equal to change in momentum. Well, here is the force time curve. As you see that the importance of force time graph is that the area which force time curve makes with time axis in a certain time interval always gives the value of the impulse of the force in that time interval, irrespective of whether it is a constant force or a variable force. Well, here is another important term in classical mechanics, that is impulsive force. We often encounter with forces of very large magnitude acting for a very small interval of time, of course producing a finite change in momentum. Such forces are called impulsive forces. Now, in such a situation, it is really very difficult to measure the force and the time separately. However, the product of force and time, which is the change in momentum of the body, can be measured. That is, the effect of impulsive force can be measured by the change in momentum of the body. So we can say that impulse of impulsive force is equal to change in momentum. Well, next comes a very important principle, what I call the principle of conservation of linear momentum, which really finds tremendous applications in theoretical physics as well as in technical fields. The statement is, if the net external force acting on a particle or a system of particles is 0, the total linear momentum of the particle or the system of particles remains conserved. Now, please note this point, that the linear principle of conservation of linear momentum is a consequence of both second and third law of Newton. Now, if you like to prove this principle, what we assume a system consisting of two particles, say 1 and 2, let F1 be the force on external force on particle 1, F2 be that on particle 2, F12 is the force on particle 1 by particle 2, F2 is that force on particle 2 by particle 1, all at the same instant t. Now apply Newton's second law for both the particles. For particle 1 we get an equation one like this, and for particle 2 this is the equation where P1 and P2 are the momenta of the particle 1 and 2 respectively at the instant t. Now add up these two equations and we come at an equation like this. This is the equation number 3, where F external is F1 plus F2, which represents total external force on the system. Now apply Newton's third law to equation 3. F12 and F21 are the action reaction forces, so the F12 is equal to minus F21. Then equation 3 reduces to the form F external is equal to time derivative of P1 plus P2. Now if we put F external to be 0, then time derivative of P1 plus P2 is equal to 0. That is, we can say P1 plus P2, which is the total momentum of the system, which remains constant in time, that is conserved. So we can conclude that if no external force acts on the system, the total linear momentum of the system is conserved. Well, now I am going to discuss two very important practical applications of conservation of linear momentum principle. Number one, the recoil of gun after firing a shell. Now, when a gun fires a bullet, the gun imparts a momentum to the bullet, and as a result the bullet moves forward. The bullet in turn imparts equal backward momentum to the gun at the same instant, due to which it moves back with a velocity, what I call the recoil velocity. Now, as no external force acts during the whole process, the momentum of the system remains conserved. Now, look at this figure. Before firing, both the bullet and the gun are at rest, so the total momentum of the system is 0. Immediately after firing, small v is the velocity of the bullet and capital V is that of the gun. So total momentum of the system immediately after firing is capital N into capital V plus small m into small v. That is equal to the initial momentum, which is 0, and we get an expression of the recoil velocity of the gun in the form of equation 2.5. The negative sign in this equation simply implies that the direction of the velocity of the gun is opposite to that of the bullet. Now suppose we have a machine gun firing n number of bullets per second. Then the total momentum imparted to the gun per second, that is the force exerted on the gun, is given by this formula. Also, we can have a comparison between the kinetic energy of the bullet and that of the gun, and it can be shown that kinetic energy of the bullet is more than that of the gun. I am leaving this topic as a task for you to prove. Well, the second application is the rocket propulsion, a very interesting application, and is an example of motion of a system of variable mass. And the phenomenon of rocket propulsion is also based on the principle of conservation of linear momentum. Now you see, as the fuel is being burned continuously, the mass of the system of rocket and fuel goes on decreasing. The hot gases produced due to burning of fuel are ejected in the backward direction from the tail of the rocket with very high velocity and of course with very high momentum. The ejected hot gases in turn impart momentum at equal rate to the rocket in the forward direction, and the rocket moves forward. As no external forces act on the system except the action-reaction for internal forces, the total linear momentum of the rocket gas system remains conserved. Now, detailed mathematical formulation in this case is beyond the scope of our syllabus. However, we can frame up an equation using the principle of conservation of linear momentum. As you see the figure, this is the situation at the instant t. M is the mass of the rocket plus unburnt fuel, and v is the corresponding velocity of the rocket. After time delta t, delta m is the mass of the fuel burnt out. As a result, mass of the rocket plus the unburnt fuel becomes m minus delta m, and the corresponding velocity becomes v plus delta v. So delta m is the mass of the gas being ejected out. Then we could write this equation: mv is the total momentum at the instant t, and this is the total momentum at the instant t plus delta t. The negative sign in this direction in this equation is due to the backward velocity of the ejected gas. Now, using this equation and replacing Ug by Ur, which is the relative velocity of the ejected gas with respect to the rocket, and considering the effect of gravity also, we can arrive at the expressions for the instantaneous velocity in the form of equation 2.7, instantaneous acceleration in the form of equation 2.8, and instantaneous thrust on the rocket in the form of equation 2.9. Don't get scared about the negative signs in these two equations. As you know, this delta m by delta t is the rate of change of mass, rate of consumption of fuel, which itself is negative, which in turn makes both A and F positive. So that's all for this session. Thank you.